Okay. Good morning, everybody. So today we will wrap up the entire convergence and tail behavior properties. So the reason why I'm actually stressing this a little bit is because unless you actually start thinking about how rapidly or how slowly things converge, you may think, well, 10 observations are good enough to estimate 10 parameters, and then you afterwards be very sad if your 10 parameters are not very accurate, right? So that's precisely why it actually helps, even in a very simple toy case like estimating averages, to see how well this really converges. So what we did on Monday is we looked at essentially asymptotic behavior. So we asked questions like, do averages really converge? And if they converge, how rapidly do they converge? Today, we'll look at finite sample size bounds. So basically, today we'll ask, how many of those observations do you really need until you're close to that limit distribution of a Gaussian, right? Is it just a coincidence because I picked, the uniform distribution over the unit interval that this converges so rapidly? Which additional assumptions do I have to make? And the reasons why you care about this is something very practical called A/B testing. So some people on LinkedIn put A/B testing as their specialty. If they're doing A/B testing, they do exactly what we covered in last lecture and this lecture. If you understand those two lectures, you can probably get a job as an expert in A/B testing. Okay. It's not a very high bar, and by now companies should be doing better than that. But anyway, so the simplest first thing that we can do is we look at something called the Markov's inequality. So basically, suppose that I have a random variable x which has some mean mu. And what I want to do is I want to check what the probability is that this random variable x exceeds mu by some extent. So, or rather that x is larger than epsilon. And this can be proven actually very easily. And obviously, if epsilon is less than mu, then the entire argument is pointless, because I could always just pick a distribution which has a point mass, right? So if this is mu, and all I do is I just put the point mass here. So asking, in general, what the probability is that I see something over here, that's of course nil. I can't really get a useful bound on that. However, I can, in general, immediately bound what the chances are that you exceed the average by a lot. It's not an amazingly strong bound in its own right, but it's actually a good vehicle to, get other results as part of it. Oh, wow, didn't know that. So let's prove it. So after all, we are interested in the probability of x exceeding epsilon, right? So that's the integral going from epsilon to infinity dp of x. Now, since I know that x is going to be greater than epsilon, x over epsilon is definitely going to be greater than 1, right? So this quantity here is greater or equal than 1. So I can just plug that in. Then I go and pull 1 over epsilon out, and I get the integral from epsilon to infinity dp of x, which is of course again upper bounded by the integral going from 0 to infinity. And if I have some non-negative random variable, then, that's exactly the mean. Yes?
So when you say we have a non-negative random variable, we're just assuming that x is always positive then, and that's why we can
Correct.
start at 0?
Now, of course, this is actually what I was going to ask next. Well, what happens if x can be negative, right? Well, two things can happen. First of all, if mu ends up being negative as well, then the entire bound becomes pointless, right? So without loss of generality, we can assume mu to be non-negative. Now, of course, the bound doesn't exactly hold anymore if x is less than 0, right? Because then adding that additional bit to the integral here would actually make the contribution smaller. So that's why I have to assume that x is non-negative. In many cases, x is a non-negative random variable, so this is okay. So let's actually use this right away to prove Chebyshev's inequality. So the Gauss-Markov inequality is kind of really primitive. It's just like, well, p of x greater than epsilon is order 1 over epsilon. That's not particularly useful in its own right, but you can actually use this as a point of departure for a lot of other more useful bounds. So one thing that you could, for instance, do is you could say, well, suppose I know the mean and the variance. Can I get a more meaningful statement about, for instance, averages, right? So you may have seen that, sometimes people will plot the mean plus minus the variance. Sometimes they will plot plus minus 2 variances. And I think there's actually a company that's called 6 sigma, right? Which is, plus minus 6 variances. Now, how meaningful is it actually to plot plus minus 6 sigma, right? Let's work that out here. So the theorem is that the probability that the empirical average exceeds its average by more than epsilon is less equal than sigma squared over m epsilon squared. Or in other words, that epsilon is less equal than sigma over square root m delta. Right?
What is the m?
So m is the sample size, so I'm basically averaging, and delta is my failure probability. So in other words, if I tell you, well, I want to get something that holds with confidence 95%, right? And delta would be 0.05. M would be the sample size. Let's say I have, 100 observations. I know sigma, maybe sigma is 1. And so I plug this in and I get a confidence interval within which I can expect my random variable to be. So I'll get an epsilon. So what we're seeing here is already a non-trivial interaction between 4 key quantities that we'll always see over and over. So there's a confidence interval, epsilon, which is basically, how tightly, if this is, my mean, how tightly I want to get my guarantee. There's a sample size which tells me how many averages I'm taking. In a confidence interval, confidence bound, confidence probability, with which you want to make sure that this test doesn't fail. So if you recall the jelly bean example, we said delta equals 0.05. And what you can immediately see is, in this case, is that if I make delta really small, then 1 over square root delta is still quite large. As a matter of fact, this bound is really horrible for very high confidence estimates. And we'll afterwards see how you can make this a lot better. But if delta is sort of, 1/3 or something in that order, this is actually a pretty good bound. And sometimes people use the Chebyshev inequality as a stepping stone to get some other tighter guarantee. So for instance, if you do things like you work on data streams and sketches, you may know the AMS sketch, so the Alon, Matthias, and Szegedy sketch, and there they actually use this type of reasoning where they then combine this with what we'll see later on being called the Chebyshev bound to get a good guarantee for deviations. Okay, so who wants me to prove the Chebyshev inequality? Okay, that's a fair number of people. Okay, so let's prove it. And we're going to prove this by just plugging the Gauss-Markov inequality in for a new random variable, which is now y equals x minus mu squared. So let's do that. Document camera. So let's just simply follow the recipe. So the new random variable y is x minus mu squared. So we know that the expected value of y is what? Sigma squared, right? Okay. So therefore, the probability that y is greater than epsilon is less equal than the expected value of y divided by epsilon. Actually, let's make this epsilon squared because it'll just make life easier afterwards, right? So that holds in the same way. Okay, now this is nothing else than sigma squared over epsilon squared. And what we wrote here is simply the probability that x minus mu exceeds epsilon, because I can take the square root and the condition still holds, is less equal than sigma squared over epsilon squared. Okay. So this is Chebyshev's inequality. Now, where did the m come from, right? Because we had sample size in the entire argument. Well, that's very easy, because what I've now done is I've defined xm to be the sum over little xi, I going from 1 to m, 1 over m. And we know that the expected value of xm, capital Xm, is also mu. And furthermore, we know that the variance of xm is what? We did that last week. We did that on Monday. So who remembers what the variance is if I average a bunch of random variables? That's true for the standard deviation. For the variance, it's sigma squared over m. Okay. So now, what we get is, just plugging this back in here, we just get delta less equal to sigma squared over m epsilon squared. And if I massage that appropriately and take square roots and all that, I get exactly this condition here. Okay. That's what we had. So, it's very, very easy to prove this thing. It's really just, following the recipe. Okay, now let's do something a bit more fun with it. So let's look at the scaling behavior, right? So for Gauss-Markov, what we have is that epsilon goes like 1 over delta. So that's like 1 over this probability. In Chebyshev, we get something that's a little bit better behaved. We basically get that, epsilon goes like sigma over square root sample size delta. By the way, you realize that in Gauss-Markov, if I take averages, I get absolutely no improvement in my confidence bounds, right? Because the mean remains the same. So I didn't win anything by averaging. And this is intuitively wrong, right? It's intuitively quite clear that I'm losing a lot by just applying such a, very brutish inequality. So I need to use slightly more refined reasoning. But actually, using Gauss Markov in order to obtain Chebyshev, I now at least get something where I have, as it turns out, the correct sample size behavior. So 1 over square root sample size is a rate of convergence that you will see over and over and over. So this part is good. The part that is bad is that one here, the one in delta. 1 over square root probability is still a very, very expensive scaling. Because you're basically now trading off sample size with probability linearly. Okay.
What do you mean by scaling?
What I mean by scaling is, oh, thanks for asking this question, by the way. Well, if I have an inequality, then I can ask, how do the various terms in my inequality interact with each other? So, for instance, if I give you not 10 samples, but 100 samples, how much more confident can you be that the same guarantee as before holds? Or how much smaller will my epsilon get if I leave my confidence guarantee the same? So if anybody here has ever done physics, you probably know all those natural laws of physics like, PV equals NKT, and essentially conditions which connect several variables with each other. And those things allow you to see what happens if I change one knob, how does the rest of the system have to adjust if I change that knob. The same thing happens here for probabilities. Because, for instance, if you afterwards want to deploy an A/B test, then you may have to tell your manager, well, this is going to cost us X dollars, right? Because we will have to test this on 10,000 users, and probably in the process of doing so, we will lose maybe 10 users because they will be really upset with what we do. And you put a dollar value on that. And then you can actually make an educated decision before the test whether it's worth doing. So this sounds kind of trivial, but if you're in the business of testing drugs, right, and you administer a new experimental drug to a patient, you want to find out very quickly whether you're killing the patient with that drug, right? So these things that I'm now, just looking at, in terms of, well, look, here's a pretty theorem. I mean, those things kill if you use them wrongly. So it's really in your interest, especially if you're a biologist, to do this. And if you're ever going to go to any internet company, they won't kill, but they will cost a lot of money. And then if you lose a lot of money, then maybe somebody will get very upset at you. So here's the prototypical bound that is actually more accurate. This is called a Chernoff bound. And Chernoff bounds come in all sorts of shapes and forms. And if you, for instance, go to Wikipedia, you will see probably 10 different inequalities with the name Chernoff bound written out. And they are all very similar. They all have more or less the same behavior. The one I'm going to derive here is something that's actually fairly easy to derive. I mean, the entire proof is on, it's 2 lines. So I want you to go through the proof with me, because usually a Chernoff bound is this big scary beast that you invoke and you never know where it came from. And most proofs are more than 2 lines. So it took a while to find a very compact one. Okay. So for that, I need to introduce something called a KL divergence. Who has ever heard of the Kullback-Leibler divergence? Okay, cool. Those of you who haven't, don't worry, we will cover this in a lot more detail in the recitations. Because this holds not just for 2 numbers, P and Q, but it holds for entire distributions. And the big difference is then that you basically sum this term here over all possible locations, right? And you can essentially think of this in an information theoretic sense as the extra number of bits that I need to encode things with a wrong code rather than the correct code. So this is essentially what you end up doing. So basically, in this particular case, it's basically the extra number of bits that I need to use if I use Q to design my code as opposed to P, which is the true distribution that I really should be caring about. And it's not very surprising that those extra bits come in my guarantee. Okay. And so first, let me actually tell you what the bound says. It says that the probability that the sum over a couple of coin tosses, so biased independent coin tosses, which are drawn with probability P, that this exceeds n times Q is so Q is basically what I'm assuming instead of P, that this is less than e to the minus n times the KL divergence between Q and P. And that actually makes intuitively a lot of sense, because that's basically e to the minus number of bits that you'll need to encode that strange event. Right? And then, and this is what I'm not going to prove, I'm not going to prove that the KL divergence, so K of Q and P, is upper bounded by P minus Q squared. This is something called Pinska's inequality, and there's a lot more and amazing stuff that you can do from this as a point of departure, but I'm going to just accept that without proof. So basically I'm going to upper bound this by 2P minus Q. Okay. This is Pinska. Okay. So now we're going to prove the first part of the statement. Okay. So, and without loss of generality, I'm going to assume that Q is larger than P, and I'm going to set K to be greater or equal than Q times N. Okay. Okay, that's basically sorry. So this is basically the number of events extra that I would be seeing or more. Okay. So the ratio of the probabilities that I'm seeing K events given the distribution Q versus that I'm seeing K events given the distribution P, well, that I can just write out. I mean, basically all the binomial coefficients cancel out, and it's just Q to the K, 1 minus Q to the N minus K, P to the K, 1 minus P to the N minus K. So I know that K is greater or equal than Qn, and furthermore, I know that Q is greater than P. Right? These are basically the two assumptions that I made here. This one here, and this one there. So therefore, first of all, for the first two terms, these two guys, I can upper bound Q to the K by Q to the Qn. Because I'm just making this exponent smaller and making this one smaller. Since this ratio is greater than 1, reducing the exponent will only make the entire term smaller. Okay. Now this ratio, on the other hand, is larger than 1. Yeah. So, no, sorry, this is smaller than 1, right? Because Q is larger than P, so 1 minus Q is smaller than 1 minus P. Okay? And now, again, instead of K, I'm replacing this by Qn. Okay? So this is also straightforward. And again, this just becomes a tightening of the inequality. Now, once you go and actually pull N out of this entire mess here, and take logs of it, you will see that you get exactly the KL divergence. You will get exactly that. Does somebody need me to prove this equality here? Does somebody want me to derive it?
I don't get what you have to do.
So, okay. Good. Who else is, by the way, thanks. This is very, very brave. Thank you. Who else got lost right from the beginning? Okay. Good. Not good, but good. So here's the thing that we want to do. We want to prove a better bound on how rapidly empirical averages converge to their mean. And we're going to take the simplest of all possible cases, namely, we are just going to take the case where we have coin tosses. So I get an outcome of 1 or a 0, right? And I want to see how far that coin toss of 1 or 0 deviates from its expectation. So remember, that's how we started out with, where I said, well, I'm tossing my coin 100 times. Rolling the dice 100 times. I'm seeing a 6 only 7 times or 11 times. What are the chances that the dice is tainted? So what I therefore want to do is I want to bound the probability that I'm seeing things where the averages exceed the empirical averages exceed the expectation by a substantial amount. That's this thing here. So I want to bound this probability. And the Chernoff bound is exactly that line. That's the Chernoff bound. It says that the deviation between empirical average and expectation, so that's n times q, or expectation for a higher bound, that this is nicely upper bounded. And we're proving this. Okay. So is everybody on board with what we're trying to prove? Not necessarily the proof, but what we're trying to prove. Okay? Any questions about what we're trying to prove? Yes?
One question. Is there a particular reason why you have to write it in terms of the sum instead of the average itself? No. By the way, it's a very good question. So what I could do is I could go and rub this out here, and I could just write 1 over n there. Right. The reason why I didn't do this is because afterwards I want to work out things directly here, right? For the sums. So, by the way, this is a very, very good question and a very fundamental one. Any logical transformation of the thing that's within the probability brackets that leaves the outcome the same, of course, leaves the probability the same. So in other words, if I say, what's the probability of rolling a 6? Or if I say, what's the probability of not rolling a 1, not a 2, not a 3, not a 4, not a 5? Right? Those two things are the same thing. So if they're logically equivalent, they have the same probability. That's all I'm doing. Okay. Now, of course, here, I can't go and divide by n because that actually means something in the bound. Okay, so good. Now we're all on board with what we're trying to do.
Why are you allowed to say without loss of generality that he was rid of it?
Okay, so if that were not the case, that's a good question, yes. What I could always do is I could define q prime to be 1 minus q and p prime to be 1 minus p. And so now I have the opposite case, and the inequalities go accordingly, and then I can just work it out directly there. That's, for instance, one way of doing it. The other thing is you can actually get corresponding lower bounds as well. The algebra looks a little bit different, right? So, for instance, sometimes when you look up Chernoff bounds, you will actually get different statements for the upper and the lower bound. Here we are being extremely lazy, and we are just writing something that will actually hold from above and below. But for instance, if I have a probability of 0.05, chances of seeing -1 events, well, that doesn't exist, right? So you would expect that at the tails, things behave differently. And sometimes in learning theory, when people ignore this, then you get very weird behaviors at the extremes where I have almost zero error. You get all sorts of pathological cases of different bounds that all of a sudden look very different between whether I have 0 errors or 1 error. This, for some time, was the case when people looked at VC bounds for support vector machines, and they measured the number of support vector training errors that they got. And there was one set of bounds that worked for 0 error,
and there was another set of bounds that worked for non-zero errors. And they looked very different. And that is just due to essentially a pathological fact of the mathematical reasoning that was used in order to obtain the bounds. And it had absolutely nothing to do with reality. Okay. There was, I think, another question, right? Okay. Yes?
Sorry, just to make sure, P is the imperial. Q is the expected.
No. It's the other way around. So P is the truth, but I don't know the truth, right? But what I know is I can say, well, you know, I can just pick Q. And so what we need to do is we need to see, you know, how P and Q differ from each other. I mean, as a matter of fact, for the entire reasoning here, it doesn't really matter very much which one is the empirical, which one is not. It's basically just a statement about drawing from a distribution with probability P and using Q as my yardstick. Sorry, I still have a cold. Now, the first thing that I need to do is, basically I just need to bound the ratio between drawing K observations under Q versus drawing K observations under P. That's basically all I'm doing here. And I need to basically lower bound this. So the first term is just really plugging in definitions. There's absolutely nothing in there that you shouldn't have seen. For the second thing, all I'm exploiting is just that if I have a number that's greater than 1, then reducing the exponent will make it smaller. And if I have a number less than 1, then the opposite will happen. Right? That's basically all that I'm doing here. Right. So now, then all I have to do is just, you know, collect terms here. So you see an n occurring everywhere. And then just pulling that out, and you get exactly the KL divergence. Now the cool thing is how we use this, right? So what I'm after is the sum over all the events, K greater or equal than n times Q. Right? I'm after this expression here. I'm after the sum over all the probabilities starting from n times Q up to, well, basically n, of, you know, the probabilities that I'm drawing K observations. It's basically, I'm summing over n times Q up to n. Now, this quantity is exactly what we bounded here, right? And so I know that this is upper bounded by drawing, not using Q, not using P, but using Q, right? Times e to the minus n times K, KL divergence between Q and P. That's what we had here. And the minus just comes because, well, I divided, right? So I'm just pulling P out and dividing by the exponential. Okay? Pardon? This term here, this is the sum K greater or equal than n times Q of the probability of x of the sum of the xi's being K under the assumption I'm drawing from a distribution P. Okay.
But K is like continuous?
No, K, if I'm tossing coins, would be an integer like 1 or 2 or 3 or 4 or 5.
It's a sum, not average.
Well, this is a sum, yeah, because it's a sum and not an average. That's why it's a sum, right? This is exactly why I said before, I do not want to use an average, because otherwise that expression would get less fun. So xi's are just zeros or ones. Yeah. Right? And I'm summing over the xi's. And so it can be K, or, you know, K can be n. It has to be greater or equal than n times Q. Now, n times Q need not necessarily be an integer. This can be a real number. let's say it's 3.2. In that case, the sum starts from what number? So if n times q is 3.2, from what number starts k? 4, exactly. Good. So now we have that. So now the only thing is, here I have a sum expressed with conditions expressed in terms of q, and here I'm conditioning on p. And I just need to switch it over to something that sums over q, which I can make use of this inequality. Right? And then, well, now, if I sum over all the k's, and, then this has to be upper bounded by 1, right? Because if I'm drawing using distribution, using probability q, if I'm summing over all possible events, what's the sum over all possible events? It's 1, exactly, by Kolmogorov axioms, right? So therefore, I can upper bound this, and this may be very loose in some cases, by e to the minus n times KL divergence between q and p. That's it. That's the entire proof. So yes, it's 2 lines of math. And by all means, download this, look at it. Sorry, occasionally we have to do math in class. This was the hardest slide probably for a couple of weeks. Yes?
So when we get to the end of this, we say we're bounding this by the xp to the negative n divergence, but we still don't actually know p. So
that's correct.
How do we use that inequality in practice?
Very good question. And we will actually go through this in a couple of examples on the next few slides. So we will use basically, what you can already see is that if we have the statement here in terms of an average, right? Then I can, for instance, make q equals p plus epsilon, right? So then I get e to the minus 2n epsilon squared. And so now I essentially get a statement which says, well, if the empirical average exceeds the true expectation by more than epsilon, this can only happen with that probability. Right? So we will explicitly make use of that, and we'll actually go through this for A/B testing. Okay. Now, the Chernoff bound was still relatively easy to prove. The one thing that's a little bit less easy to prove then is McDiarmid's inequality, and it basically says that the same thing holds in a much, much more general case. So basically, what we had before is a statement between an expectation and a function of, in this case, m random variables. Right. That function was a particular simple function because it was just an average, right? So this thing here was a particularly simple function. It was an average. But you could think of a lot more complicated functions than just simple averages. And you could ask, well, will for those not so simple functions a similar thing that's called concentration of measure happen? So concentration of measure is the technical name for what's happening, namely that if I have an average, or if I have a function that depends on many independent random variables, then the typical behavior that I see is very close to the expectation. Okay. And that's basically what McDiarmid's inequality states, namely that the probability that f of x1 through xm is close to its expected value, so that means it exceeds it by more than epsilon, is less equal than 2 e to the minus 2 epsilon squared over c squared. Okay. Now, basically, this should look very familiar to what we saw on the previous slide. We had, if you remember, basically e to the 2 m epsilon squared, right? And this was just for a one-sided inequality. This one here goes on both sides, right? So we have an absolute value here. This is where the 2 comes from, because you need to bound it from above, you need to bound it from below. You sum them up, you get a factor of 2. Now, the one thing that looks different is we have a c squared here, and there we had an m, right? That's the one term that actually differs quite a bit. And it turns out that this c squared is given by basically bounds on the deviations that you can have by just changing one term at a time. So when you want to apply McDiarmid's inequality, what you basically need to establish is that if I change only one argument in this function f, then I will not have a large deviation in the outcome, or at least not on average. I can have larger deviations on some terms and smaller on the other ones, but this is basically what governs the stability of f. Yes? Is this what? It is way stronger than the Markov inequality. Thanks for asking. We will actually work through all of those afterwards in a special case where we just look at A/B testing and what happens if we apply one or the other inequalities. And you'll actually have fun with things like that also for the homework. Yes?
Actually, if we take f as the sum,
Exactly.
we get exactly the same.
That is exactly right. And this is what Höfting's theorem does, right? You can prove Höfting's theorem independently. This is perfect what you said. Thanks. So, as a matter of fact, if we have 0, 1 valued random variables, and if I take an average, then of course what I will get is that the deviation between, flipping one of those guys is going to be 1 over m. So this would be 1 over m. So therefore, c squared would be 1 over m, right? So therefore, 1 over c squared would be m, and we'd get exactly this correspondence, right? So sometimes when you have a statistical estimator and you want to show robustness and so on, which is basically the fact that changing one variable doesn't change the rest a lot, then you get exactly that behavior. Yes?
Apart from the fact that the expectation has to exist and the CIs have to be finite, is there any restriction on the function f?
No. So people have used that a lot also in combinatorics and so on. So this is a very popular inequality in theoretical computer science. That's why I'm showing it to you, because you will almost certainly be able to use this in some not insanely complex scenarios where at least you can assume that each of the individual outcomes are independent of each other, where the random variables are independent. The case where this does not hold is when the xi's are not independent of each other. So in that case, there are other inequalities like by Ledoux and Talleyrand. So there's they both have written extensively and great books on that subject. This is way beyond a 10701. So we're going to skip that. Okay. Now let's look at the scaling behavior. And by the way, Höfting's inequality and the Chernoff bound in this case look exactly the same. The only difference is that we proved the Chernoff bounds for 0, 1 valued random variables, and Höfting just assumed that things are bounded. So let's actually see how this compares to Markov, right? So let's set delta to be the probability that I have an excess of more than epsilon, right? And that, of course, by just plugging in the bound is, 2m epsilon squared over c squared. What's the value of c for a 0, 1 valued random variable? Well, I know that you know, but does somebody else know?
It's 1, right? So C is basically the range of that variable. So of course, if a random variable has a bounded range, its expectations exist, the variance exists, basically all the higher order moments all exist. When I don't have that guarantee, the analysis gets a lot harder. And so now what I can do is I can simply solve for the arguments in the exponential. So I just get log delta over 2 is less equal than minus 2m epsilon squared over c squared. And I can solve for epsilon. Now what we have here is epsilon is less equal than essentially some stuff, and then it's negative log of the probability divided by m, and it's the square of that. So in other words, epsilon is order of minus log delta over m. You will see a lot of those types of inequalities in pretty much any theoretical analysis that has to do with averages. Very, very rarely will you see a case where your guarantee goes like 1 over sample size rather than 1 over squared sample size. And so if you compare to before we have basically that the confidence delta and the confidence interval epsilon, they interacted linearly with each other. Now we have a logarithmic dependence. So this is, of course, way better. So if I want to make sure that if I deal with cases where delta is very small, I really want to have one of those logarithmic tail bounds, or exponential tail bounds, how they're sometimes called. Okay. Let's look at how this actually goes. There are more tail bounds, and I'm just going to skip over the slide because we already spent a lot of time on the rest. Wikipedia has a fairly good collection of them, and yes, you should probably at some point look at just what's out there. And when you're trying to prove something, use that just like an inventory of, well, let's try one of those bounds. Very rarely will you be in a situation, unless you're a good theorist, where you actually have to prove your own tail bound. Most of the times, you will be using those tail bounds to show something. Okay, so now let's actually use this in practice. So the issue is, as already promised before, we have two possible web page layouts, and I want to find out which one is better. Half the users see the design A, and half the users see design B. And how many trials do I actually need to decide which one is better? And let's say, to make life even easier, that P of A is essentially known, right? So what I mean by is essentially known is P of A is the old design and B is the new design, and I want to find out, is the new design an actual improvement over the old design? Because for all I know, it could actually make things worse. Pardon? What is P? P is the probability. By the way, given those questions, you should urgently look at a introduction to just basic probability textbook, or look through past recitations. So, because we will actually be using things like probabilities quite a bit throughout in this class. This is kind of the language of this class. And I mean, basically I need to make sure that everybody gets something out of this class. So I can slow down to some extent, but I don't want to bore everybody else. So I have to essentially adjust for that. Yes?
P of A here is the probability of the user C design A, or is it the probability of the user?
Yes, that's exactly what I was asking.
Oh, so A and B are the probability. So A is the outcome that is the probability that the user will actually, well, maybe buy something or do something desirable if I show him version A. And well, I'm interested in, will B do better than A?
It's basically a hit rate which.
Yeah, it's basically like a click-through rate. And of course, so actually this was a little bit sloppy. What I should have said is, P of A conditioned on showing this version, and P of B conditioned on showing that version. Right? So I was a little bit sloppy here in my notation. That's correct. Thanks. Okay. So essentially, I want to find out very quickly, is the new version really better? That what? Well, A and B are, okay, can I assume that A and B are independent? Well, it's a very good question. There's a couple of things where this may not be the case. For instance, it could be that some blogger posts on his webpage and says, well, Facebook is trying out a new webpage layout. Sign up for the new trial, right? And then maybe a specific group of users will sign up for the new trial, and maybe they are the more ambitious ones, and maybe they will like it. And in this case, you can actually skew things quite a bit. Furthermore, it could very well be that the click-through rates in the morning are much higher than in the evening, right? So there could be all sorts of conditioning factors. So that's exactly the kind of mess that you need to take care of in practice when you run the experiments. For instance, you may want to go and make sure that at all times you are sending an equal fraction of opportunities to both users. So you can't just go and say, I'm testing layout A in the morning and layout B in the evening. This would be a total recipe for disaster. So you need to make sure that all the other things that could possibly influence the click-through rate are the same. So this is, for instance, why sometimes you don't get to sign up for new trials for product releases. Because you're in the control group, right? And it would be messing up the estimates quite a bit if you could do it otherwise. So this is why for a very first rollout, maybe you can get 100 or 1,000 volunteers just to find out whether it works at all. But then you may very well randomize rollout. So for instance, when Google rolls out Android, you will see that not everybody gets Android, the new update at the same time. Some of this has to do with making sure that when a new version of Android is rolled out, not everything blows up horribly for all the users. You want to have a staged rollout. I don't know whether Apple does the same thing, but I presume they probably would, where you don't let everybody have the new version at the very same time, but maybe over a couple of days, such that you can prevent major disasters if something happens. Okay, now let's actually look at what happens. So my goal is to find out whether the new layout is at least 1% better. So what I need to do is I need to bound for a deviation of 0.01. So I'm actually giving you a lot more information than what you typically have. And so the worst thing that could happen to me is that P of B is exactly 0.11. So it's right at the boundary. And I want to have a failure probability of 5%. In other words, only in 1 in 20 cases things can go terribly wrong. So now, if I use Chebyshev's inequality, so if I have no prior knowledge, right, the only thing that I can really do is I can bound the variance by sigma squared is a quarter. Well, why is that? Well, that's basically just the variance of a binary random variable. Right, so if you work out the variance of a variable that can either give you 0 or 1, you will see that the maximum variance that you can get is a quarter. Sigma squared is a quarter. Okay. So then, all I have to do is I just work out m has to be less equal than sigma squared over epsilon squared delta. Sigma squared is a quarter. Epsilon squared is, 0.01 squared, because that's basically what we need in the deviation. And delta is 0.05. So in other words, I need 50,000 trials before I can safely establish that version B is better than A. Now, if I know that the click probability is at most 15% for the new layout, and that's a sensible assumption that basically
the old layout wasn't too bad, and the new layout isn't going to break any records. And in a way, if it breaks records, I'll just detect it way more quickly anyway. So it's not too bad. So then I can actually get a tighter bound on the variance. So rather than a quarter, I get basically that it's about 1/8. In that case, I can see that I need about 25,500 users. So you can see that very simple additional assumptions that I can make on my random variables can drastically reduce the cost of the experiment. Yes?
In reality, how many of these variables do you actually have in your hand, like solving this problem?
Well, it depends on how much time you spend with essentially your web page designer. No, I mean, this is literally the case. When you want to build such a system in practice, you want to talk a lot with the people who actually build and roll this thing out and get very good estimates and bounds on how things behave before. So this is why you always want to log things if you're running a web service. Log as much as you possibly can. Because all of those uncertainties that you have otherwise will cost you extra money. So for instance, if you didn't know how A behaved either, you would actually have to establish, the confidence of A, in the same way. And in a way, that's what you're going to do in the homework. You will get 41 shades of blue. Now let's use Höfting's bound. So in this case, well, the random variable has, bounded range. Okay, click or no click. So C equals 1. It's kind of ham-fisted. And we just plug in Höfting's inequality. And so what we get, again, same epsilon, is basically 18,500. So this is a little bit better than Chebyshev. So what you can see already here is that by using different math, I can do things more cheaply. Okay. Now, can we do even better? Well, we could cheat. We could say, well, given what I've seen before, over 10,000 observations, this is crazy much anyway, so we're essentially in the asymptotically normal case. So let us just fake it and use a normal approximation. Because I know that in the limit everything will be Gaussian. That's what we already established on Monday. So let's just, take a Gaussian interval that contains everything, that contains a 95% probability range. So what I basically have to do is I have to ask, what is the integral, the Gaussian integral, going from the mean minus epsilon to the mean plus epsilon that has a value of 95%. And then what you can do is you can actually read this off. So there are tables which will tell you if I want to have 95% probability, then how far out do I need to go relative to the variance? And so I can just read off that epsilon is 2.96 sigma. Okay. And then, well, I go and, use the variance bound that we had before. So basically around 0.1275, because I assume that, the variance isn't going to exceed, so that the, click-through rate isn't going to exceed 15%. So this gives me that bound on the variance, right? And I just plug things in. And what we get is something even smaller. Here we get basically 11,000 tests. Now, I can do even better by getting tighter bounds on the variance. I can do a lot more other things. But this should just give you a little bit of a flavor of how different math can actually drastically affect, how many people you will kill with your new drug, or how much money you will spend, or, how quickly you can actually develop new things. Now, real life often isn't quite that simple, right? Because you're usually not only going to make one step forward at a time where you test, layout A versus layout B. Quite often, you may have 10 or 20 different aspects that you can try out. You may want to test them out simultaneously. So what you will probably find is sometimes that when you look at your Facebook
web page layout and then your friend's Facebook layout, then sometimes they differ in very subtle ways. Sometimes it's just maybe, you know, how wide things are, how many pixels wide, maybe the font is slightly changed. And basically, those tiny, essentially imperceptible variations are often indications that somebody's running an experiment while you're using the site. And that's just because often it's so much easier to simply go out and test things, but then you still want to be able to actually use a fairly efficient mechanism in order not to test too long, such that you can actually deploy very quickly. And by the way, this is not only Google doing that. At some point, Microsoft did a similar thing for their Bing search results. And essentially, the bottom line is higher contrast was better than lower contrast. Yeah. But it helped. And they actually got a much higher click-through rate through that. And yes, okay, user happiness improves, and maybe people come back more to Bing. Who knows? But the point is, this is not necessarily a nefarious thing. You're really doing this to, well, maybe save money, maybe to cure people, to improve your web page layout. Of course, this is also what's happening with ads, right? Because I basically, if I have the choice of showing 100 different ads, then I need to decide which one I'm going to show, and which one I'm going to show sufficiently quickly, such that I don't end up losing a lot of money. Okay. So this essentially, the logical extension of this is what's called a bandit algorithm, where you, for instance, sent to a casino and told to gamble. This is in the old times when you couldn't actually screw people with computers, but you had real mechanical bandits, and they had slight variations in terms of, you know, how likely they were to give you a reward. And you wanted to find out as quickly as possible which of the bandits was the best one, such that you could gamble the rest of your money away on the bandit that actually took the least. And there's very beautiful math. We may or may not have time to cover this in the class because just the amount of content, but this is a really exciting area also to read up, and there's another logical extension which is reinforcement learning. So there's a lot more that can be done there. We will probably not have time for that in 10.701. Okay. If the cameraman could please stop the camera for a moment.